Keep it away from my cell phone.
All right, get started. Steve, take it away.
Okay, thank you, Matthew. The parts of lecture 2 that I didn't finish, you can read on the web. And we're going to jump into lecture 3, where we learned last time about some of the gates that we can do that you could use in a quantum simulator. And we're going to learn some more gates today, and then we're going to apply those ideas to study the photoelectron spectra of triatomic molecules via boson sampling. So I'll explain what that all means. So the idea, I have, say, water, and these hydrogen bonds can vibrate, right? The proton can move in a potential energy surface that changes as the chemical bonds stretch and shrink. And you can have a stretching mode and a bending mode. And we want to study the non-equilibrium, in the spirit of the theme of the school, non-equilibrium vibrational dynamics of these molecules. When you send in a high energy photon, suddenly ejects a bonding electron, let's say, from that bond. And it leaves behind, now the Hamiltonian will have changed for the nuclei, and it'll be left in an excited state. And so we want to build a quantum simulator where the vibrational quanta are represented by electromagnetic quanta, microwave photons, in 2 different modes. And I'll show you how that all works. And the first generation, I'm going to show data from the first generation experiment by Chris Wang in Rob Sholkoff's lab. Okay, so as we've discussed, if you want to build a universal quantum simulator, you have to have universal control of all the quantum objects in the system. You use that control to create some initial state, non-classical states. So in quantum optics, classical means coherent states, and non-classical means anything else, like a Fock state. And then you need that control to synthesize an artificial time evolution under some Hamiltonian that is not the natural Hamiltonian to the system, but one that you are synthesizing through your control. And then the reason that quantum simulators are useful is you can make amazing measurements more or less directly of, the wave function. You can probe coherences and do things that, a typical, at least condensed matter experimentalist would have trouble measuring. And so you need to be able to do state tomography, efficient and non-trivial measurements to determine how the quantum state has evolved in time. Okay. All right, so we're going to spend some more time continuing the theme of the last lecture. We're talking about how do you get control of this system. And we talked about the fact that if you have a particular mode of a microwave cavity and you only have classical controls, your commercial microwave signal generator, you can only produce coherent states. You do not have the sort of semi-classical states. You can't produce an arbitrary quantum state. You need to have some sort of auxiliary anharmonic object, in this case, a transmon qubit, which is typically not actually inside the cavity, but just sort of poking its nose in on the side here. And the anharmonicity of this structure will let you control the state of both the transmon and the photons using classical drives and produce arbitrary quantum unitary transformations. Okay. So, and we talked a lot last time about our friend, the dispersive coupling, which causes the frequency of the cavity to depend on the state of the qubit and the frequency of the qubit to depend on the number of photons in the cavity. And we talked last time about this snap gate, these selective gates that apply a Berry phase, a particular Berry phase to a particular photon number state, and you can make that Berry phase different for each photon number. And we did that by using this dispersive coupling, okay? And it turns out that this plus cavity displacements, which we're going to talk about much more today, you can show give you universal control. But for the purposes of the simulations I'm going to show you today, we're going to use this same coupling, but with a different gate set, a different instruction set architecture to use the computer science language. And this one consists of displacements of the cavity that are whose sign is controlled by the state of the qubit, and qubit rotations that are independent of the state of the cavity. So it's a little bit backwards from the other one. In the first case, in the snap case, we were doing rotations on the qubit that only worked if the photon number was a certain thing. It was controlled by the cavity. Now we're going to do operations on the cavity controlled by the qubit. Okay, so let's start first by reviewing ordinary displacements, which we also heard about in Crystal's ion trap lectures. This is the displacement operator labeled by a complex amplitude that represents how much of the displacement is in position and how much of it is a momentum boost. So we're going to use a lot of pictures of phase space of the oscillator. And I'm going to use some funny units that we call Wigner units, in which the mode operator is x plus IP without the 1/√2. And so the commutator of x and p is going to be I/2, but it's just a minor detail, okay? So if you can make these displacements, you can, for example, take the vacuum state, this fuzzy blob here, and move it over here to the position represented by the complex number alpha. And that is a coherent state, alpha. It's just a displacement of the vacuum. You've got the same uncertainty blob, it's just in a different point in space. And if Taylor series expand this, you find out that the amplitude of having n photons is alpha to the n over the square root of n factorial. And you also find out this weird thing that if you're in a coherent state and you destroy one of the photons, you're in the same state. This is the backwards version of the Hilbert hotel. So the Hilbert hotel, to explain the concept of countable infinity, a set is infinite if it can be put into it's a one-to-one mapping to a proper subset of itself. So Hilbert said, there's a hotel, it's full, and new guests arrive. What to do? Move the guest in room 0 to room 1, the guest in room 1 to room 2, et cetera, and put the person in there. This is the other way around. You want to keep making a profit. And one of the guests checks out from room 0, so you quickly move the person in 1 down to 0, 2 down to 1, and the hotel's still full, and you're still making money. This is like the light in a laser, yes, or a radio station. That's why it's considered more or less classical. Yeah, this is electric field and this is magnetic field. Thanks. Okay. All right. So that was a simple displacement gate, but it only makes coherent states. So I'm going to just first define for you this conditional displacement gate and then give you, without too much math, hints of how it works. So a conditional displacement gate is just an ordinary displacement, except there's a sigma z from the qubit here. So if the qubit is in 0, so sigma z is +1, you get a displacement of alpha. If the qubit is in 1, you get a displacement of -alpha. Well, right away, you've produced entanglement between the qubit and the cavity, right? Now, you start out, let's say, in vacuum with the qubit in the x direction. That's a product state. I apply this operator. Now, you have an entangled state between cavity is in alpha, qubit is in 0, cavity is in -alpha, qubit is in 1. Okay? So it's an entangling gate. And the other gate we'll use is just single qubit rotations around some axis on the equator of the Bloch sphere, which you get to choose by choosing the phase of the drives, just like Crystal was talking about for ion traps. So conjugating this gate with 2 of these, you can change sigma z to any other Pauli matrix or any sigma vector dot some unit vector. You can make sigma x, y, z, or anything else. Okay. The native, yeah, this is sort of natively available in ion traps, roughly speaking. It's not for us. We have this dispersive coupling, which has a preference for sigma z, for the energy eigenbasis.
But it could go one step back. You had a dagger with sigma plus and a.
Yes.
So that one is like that after rotation of sigma plus. But if you conjugate the rotation.
Well, ultimately it's going to be derived from there. But I'm going to show you how to derive it from a hand wavy way from the dispersive limit. So it turns out this instruction set is universal if you do qubit rotations, control displacements. Here called ECD for echo control displacement. That's a technical thing. Don't worry about it right now. And you alternate these. You can make any, in principle, any unitary on the combined hybrid system of a qubit and an oscillator. Okay. Okay. So how do you do this? I mean, it's not natively available. How do we generate it? Well, we're going to use this dispersive interaction that I talked about. Here's the experimental reference. And roughly speaking, I'll just explain in words what happens. What does this term in the Hamiltonian do if you have evolution under that in the interaction picture? E to the I theta A dagger A is a rotation in phase space. Okay. And it changes, this is what the Hamiltonian, if you forget the sigma z, that's what the time evolution of a harmonic oscillator looks like. It's just going around in circles in phase space, both classically and quantum mechanically. So now the rate at which it's going around depends on the state of the qubit. And I'm going to be in the interaction picture where you forget about this very rapid rotation here. So imagine I'm in the vacuum state and I make a big displacement over to here. and then this rotation turns on. If the qubit is in the excited state, maybe it rotates over here. If it's in the ground state, it rotates over there under this effect, under the dispersive interaction. Is that clear? Yep. Yes. I'm going to apply, and I'm going to do it very fast on resonance, so it doesn't care whether the frequency is omega plus chi or omega minus chi. Going to make an unconditional displacement. Okay. So that gives me a lever arm. That this can be actually fairly small, weak dispersive coupling. But if I go way out here and I change by a small angle, I actually get a huge conditional displacement. Okay. And so that actually speeds up the gate, which is good because we always want to go as fast as possible. So you wait a little while for this conditional rotation to give you effectively a conditional displacement, and then you displace back. Well, that turns out not to be exactly right. And there's an additional step where you flip the sign of the qubit and flip the sign of the displacement and kind of put in echo sequence in the middle. And it echoes out the undesired parts of the rotation and turns it completely into this controlled displacement. But the details are in the supplement of this paper, but I won't go into them here. Yeah.
One of the A's sort of, I should think it was replaced by alpha.
Yeah, so this, if you take this operator and make a frame displacement, so A goes to A plus alpha, then you can see where it's starting to do that. Yes, exactly. Yeah, yeah. So what Leo is saying is, if I take displacement A d of alpha, this transforms A to A plus alpha and A vector plus alpha star. And then if I take those expressions and plug them in up there, I get e to the minus I chi t A dagger plus alpha star A plus alpha. And you can pick out terms here, alpha times A dagger and alpha star times A, which are starting to look like possibly I have a, well, somewhere I need a minus sign. But anyway, it starts to look like this. But there's some other pieces that are still A dagger that are not so good. And so that's why we do this echo thing where we flip the spin and echo away the unwanted rotations, leaving only the translations. Yeah. Absolutely. Yeah. Other questions? Okay. All right. So, well, I have to apply to the cavity, an electric field oscillating on resonance with just the right amplitude to produce the desired displacement. How do I calibrate that? I apply so many millivolts from my microwave generator. It goes through 110 dB of cold attenuators to get down through the fridge to the thing. How do I know how big an amplitude to apply to get a certain displacement? So what you do is you put the qubit in the X state using a Hadamard gate. Then So this is phase space. Here's sitting the cavity in vacuum, and the qubit is in a superposition of 0 and 1. I do a controlled displacement so that the cavity moves to here if the qubit is in 1, here if it's in 0. Then I do an unconditional displacement. I just move both of these blobs up here. Then I do the reverse conditional displacement, and then an unconditional displacement. I came back where I started. Okay. But if the qubit is in 1, the cavity did this in phase space, made a counterclockwise loop. And if the qubit is in 0, it made a clockwise loop. And when you move in phase space, because X and P don't commute, you get a Berry phase. The cavity ends up in the vacuum, but that Berry phase gets kicked back onto the qubit with opposite, just like that. What does that do? That rotates the X state around the Z axis. So then you get a phase kickback. So it's like, this is like a atomic clock Ramsey fringe experiment. You apply another Hadamard and you convert X information into Z. And then you measure the state of the qubit as a function of the size of the push you gave with this signal generator. And now you've done, the thing which is the only thing that metrologists want to do. The fundamental law of metrology is if you want to measure something, turn it into a frequency. Okay. So as you see the period of these Ramsey oscillations, you find out that when what amplitude of pulse gave you a Berry phase of plus pi for this guy and minus pi for that guy, which returns you, which is a 2 pi rotation. So you just calibrate it using the period of this guy. So that's how we find out how big alpha is in units of volts on the generator. Yes, the area, if you use the same alphas here, then the area goes like alpha squared, but you can control them separately. It's the product of, the area is the product of the controlled displacement length and the uncontrolled displacement length. And this is a very familiar tactic also for ion trap people who have to do the same calibration, as I understand it. Okay. All right. So now let's start thinking a little bit about how in the world this gate set can give you universal control. Okay. So I showed you if you started in the vacuum, did a controlled displacement in some direction, you would end up with this. So here's qubit in 0, qubit in 1. Now let's apply some qubit rotation. So this becomes like maybe minus X. Apply a Hadamard. This becomes plus X qubit state, minus X qubit state. Now apply another controlled displacement in some other direction. This blob is a superposition of 0 and 1 now, so it splits into 2 blobs. And that guy splits into 2 blobs. Do it again, you have 8. Do it again, you have 16. And pretty soon you've you can sculpt amplitudes in phase space any way you want and produce more or less any state you want. Okay. Now, these blobs are all entangled with the state of the qubit, and the hard work comes in trying to figure out how to unentangle. If you want to just leave the qubit in the ground state and the cavity have some interesting sculpted state, there's a work to be done. So, so this is an ordinary qubit rotation. The angle through which you rotate is controlled by the amplitude times the duration of the Rabi pulse. And then the phase of that pulse determines which axis you're rotating around, X or Y or somewhere in between.
First, did a single qubit operation.
Yeah, I rotate it. So here I'm in 0 and 1. Now rotate the qubit. So let's say this becomes 0 minus 1, and that becomes 0 plus 1. Okay. And now do a different displacement. Does that make sense? So you get a hint that you can sort of do something complicated. It feels like it might be universal, but who knows? Okay. But that's sort of. Tomorrow I will talk about how to construct the lattice, the phase-space lattice of the GKP error correction code using precisely this case set. Okay. Yeah.
Previous slide. We apply a Hadamard to the qubit and leave it for a little bit of time. We can put the qubit in the ground state in the first cycle state, and the cavity will be in a cat state.
So this is a Schrodinger cat, not a cat state, a Schrodinger cat. So I don't know. This is the cat is alive, and the poison bottle is fixed, and the cat is dead, and the poison bottle is open. Right? It's an entanglement. This is the macroscopic thing. The cat. That's the small poison bottle. You need to find a way to disentangle. If you could disentangle the qubit from this state, then you would have a superposition of two current states, which is called, confusingly, a cat state, as opposed to a cat. And that is actually possible with this gate set. And, you know, if there's time at the end, maybe I could just, it's a 3 or 4 step, 3 lines. I can show you how to do it. Good. Yeah, cat state is just superposition of alpha plus minus alpha, and the qubit is factored out. A cat is this entangled state. Okay. All right, so here's a, oh, yes. No. So I want to entangle the cavity and the qubit. And the conditional displacement does that. Okay, so if you're here's the unitary. This is a displacement of the cavity, but the sign of the displacement depends on whether sigma z of the qubit is 1 or minus 1. Does that help? Oh, okay, good. All right, excellent. Let me explain why that's a displacement. Thank you. So suppose I wanted a unitary which took some state centered at 0 and made it centered at x equals delta. So this is psi of x. Okay. Well, let's Taylor series expand this. This is psi of x minus delta psi prime at x plus 1/2 delta squared psi double prime of x plus blah, blah, blah. Okay. So this Taylor series, going back to regular units where P is the generator of displacements, not 2P in the Wigner units. If you expand this exponential, you get powers of delta and powers of derivatives, because P is minus I d dx. And so this unitary produces position displacements, okay? Then there's another unitary that produces momentum boosts. Because if I have a plane wave, e to the ikx, or e to the iqx, and I multiply by that, I get e to the ik plus q. So I boost the momentum. Okay, so this guy is e to the ik a plus a dagger, okay, over either 2 or root 2, depending on your units. And this guy looks almost the same, except there's an a minus a dagger. Okay, so now a alpha a dagger minus alpha star a is some linear combination of p and x. So it's some e to the I delta p x hat minus I delta x p hat. If you write this as in terms of a and a dagger, and this in terms of a and a dagger, you get this. So that's why it's a displacement in phase space. Does that help? Good. I'm glad you asked that question. Others? Okay. All right. Imagine that I had, so in control theory, you imagine that the the thing you're controlling is called a plant, like a chemical plant, even though it might be a qubit. And you imagine you have some Hamiltonian G1 of T V1 plus G2 of T V2, where V1 and V2 are those guys up there. And you have control knobs, classical control knobs, where you can adjust those. And the question is, can I turn those knobs in a way to produce an arbitrary unitary on the system? Well, that's not exactly what we have. We have gates where we sort of have digital control, right? We have control displacements. So e to the I k x hat sigma z. We have some gate that we can do, which is like having V1 on for some time. And we have the gate for e to the minus I delta x p hat sigma z, which is like having this gate on for some time, or we can have them on at the same time. But they're sort of discrete gates. They're on or off. Okay. Well, it turns out that the way to figure out what's going on is to look at how much control you have, is to think about the commutator of the control Hamiltonians that you have. Well, this is a mixed Hamiltonian, mixing x and p from the oscillator with the Pauli matrices of the qubit. And if you say evaluate the commutator of V1 with V2, you get this thing, which is a higher order polynomial, more complicated object than the original ones. And if I take the commutator, let's say, of V1 with that more complicated thing, I get an even higher order polynomial. And this is a Lie algebra, right? These operators are elements of a vector space, and they have an operation, two of them together. A commutator produces another element of the vector space, the operator, and the algebra does not close. Just every time you take commutators, you get more and more complicated polynomials. If it doesn't close, that means if you had a way of making commutators, you could generate Hamiltonians with arbitrary complicated polynomial terms in them. And therefore, under time evolution of such a Hamiltonian, you could make an arbitrary unitary and have universal control. Okay, so that's the theorem. And how do you make commutators? Well, you use Baker-Campbell-Hausdorff. So you do a little controlled momentum boost, controlled displacement, then the opposite momentum boost and the opposite displacement. And if they all commuted, you'd get 1. But they don't commute, and to leading order, you get this thing, exponential product of these two of the commutator. So now I have a way of generating an effective Hamiltonian, which is based on, this is a unitary, which is like time evolution under a Hamiltonian, containing this more complicated Hamiltonian term. And then I just keep going. And if I have infinite time and no decoherence and perfect controls, I can do anything.
So I'm wondering if there's any fine print on this theorem, because I would imagine that just because I could generate very complicated strings of operators, I can generate any operator. Right?
Okay, I'm just a humble, I'm barely a theorist, you know, I'm like a failed experimentalist. And I'm definitely not a mathematician. But you're right, that isn't really a proof. But you got to admit, it's pretty convincing. If you're not convinced, let's step outside and fight it out. Okay, this actually is a theorem. I didn't really prove it, but it is a theorem with a capital T, I'm told. Okay. Any other obnoxious questions?
So if you have higher combinators that you want to generate, you would expect that this would be lower in, like, higher in powers of theta.
Yes, sadly, yes. Sadly, yes, you're absolutely right.
Sense that it would work provided I.
Right. Again, the theorem was stated by mathematicians.
I understand.
Yeah. Okay. But practically, the more complicated the unitary you want to do or Hamiltonian term you want to generate, you're going to have to concatenate. Like if you want to get the commutator of this with V1, you're going to have to do this BCH trick over again, and et cetera, et cetera. So it does get very hard. And there's probably theorems about the complexity you can define in some way, but it does, you're absolutely right.
What support size can go up to like that?
I will show you. So this is like a way of showing that I can make an analytic approximation and get this Hamiltonian term as long as these are really small. Okay. I'm going to show you that if you use finite values of these and string them together and then use a computer to adjust those parameters with very short circuits, you can make extremely accurate, very complicated unitaries. So that's what saves us. But excellent question and not obnoxious. Just kidding. Okay.
With no other mathematical questions, but just feels like it can fail to close in many different ways. It can fail to close and cover all the operators, or where now it still can't. There's some. It's a question of how well does it cover all possible.
I'm not going to ask you to step outside because you're a hockey player and you're mean. No, I suppose that's, I have no idea, but it is a theorem.
Theorem stated the way you stated it.
Okay, I have no idea. I heard on the street that that's a theorem. And classically, you know, it's the Lie algebra of the Poisson brackets, but yeah, I actually don't know. I'm, you know, I'm trying to get stuff done, not be rigorous. Okay. So then also, if you want to add terms, you just use Trotter-Suzuki, right? You just apply each term in succession, time, break it up in time. And so you can, in principle, assuming, except for the fine print, generate any possible Hamiltonian term and evolve the system under it. Okay, so I'll just scratch out the QED. All right.
But is this what you call universal?
Yeah, right. So now you have, in control theory, the system is called controllable. In you know, quantum mechanics, you can also say it. You can create an arbitrary unitary. You can do the most general unitary thing you can do to a system. If you add measurements to this sequence, then you can do an arbitrary quantum channel, which is the most general thing you can do to any quantum system. It's got unitary parts and non-unitary parts. Okay, so in this paper, they strung together sequences of controlled displacements and qubit rotations, and they made Fock states. 0, 1, 2, 0 you get for free if your fridge is cold. 1, 2, 3, 4, 5. Now these are Wigner functions. We'll explain what they are later if you haven't seen them, but basically they're quasi-probability distributions in phase space. And you can see they have rotational symmetry because you have definite photon number and completely uncertain phase. And they're pretty pictures. Okay? Yes. So here you see the infidelity of the theoretical infidelity of the gate sequence that was used. And this is the depth, how many conditional displacements you used. And they're not infinitesimal the way I was in deriving that commutator. They're whatever size the computer tells you to use. And you can see that the most challenging case is Fock state 5. And even after, I guess you have to do about 10 steps. But the infidelity is, you know, 2 10 to the minus 3. So this is a very expressive, in machine learning language, this is a very expressive function set. Yeah. Oh, well, you can imagine 5 is the hardest. But here you see, like, for 9, you didn't get that great infidelity even after 12 steps. Each of the colors here corresponds to which state you're trying to make. Sorry, should have said that. Well, it's supposed to end up in the ground state according to the computer. You measure it, but here I think these are the raw infidelity. You can improve the fidelity by measuring the qubit and post-selecting the ones that are in the right state. I don't think that was done here, but I'm not sure.
I'm not sure. You told us how to make a displacement state.
Yeah.
But how do you make, like, what are you controlling to make these states? Theta 1 and theta 2?
So you make a control displacement, then you rotate the qubit by some 2 angles on the Bloch sphere, then you make a different length control displacement in a different direction, then another rotation.
But now you get a lattice of coherent states.
Well, yeah, but what if they're kind of overlapping a little bit? you know,
Okay, so it's some superposition coherent state that gives you a Fock state?
yeah. Yeah. And manages to disentangle the qubit. It's sort of amazing.
And this is done like a machine learning thing that tells you.
Well, yeah, basic. I mean, it's just some simple optimization program. Yeah, exactly. And I forget exactly what, this is experimental data. I forget exactly what the fidelities are, but they're very high. Okay. What else can you make? You can make squeeze states. Here's the vacuum. Now I can make the uncertainty in X be much smaller, but by the Heisenberg principle, the uncertainty in P has to be much larger. So here's an 11 dB squeeze state. I can make binomial quantum error correction code words that Liang Zhang talked about in a small number of steps. And tomorrow I'll talk about the GKP quantum error correction code in which the Figner function states are lattices in phase space.
All this experiment data?
Yes. It's all data. Yes.
I mean, it's the wrong axis, but like, I should think of Fock state as that located by 45 degrees. No, the squeezed one isn't like, can I think of Fock state as just that, but like you squeezing along the 45 degrees?
No. If you do this, that's another squeeze state squeezed on a different axis. X plus P is squeezed and X minus P is anti-squeezed.
But somehow N and phi are canonically conjugate, so Fock state is a squeezed on N. Go to that and phi.
Oh yeah, so this is squeezing in Cartesian coordinates. You want yeah. So this is squeezed in number and totally uncertain in phase.
Like that.
Yeah, exactly. Yeah. Good. Okay. So it turns out that the squeezing we're going to need for our molecular vibration quantum simulation experiment. Okay. And it happened, I chose with malice aforethought the two control things, which are our two generators of control displacement. Their commutator is exactly the squeezing operator. So how do I know that? Well, so last year for the first time, I discovered there's this thing called classical mechanics. And last year I taught it for the first time in my life. Wow, I learned so much. Okay, so this is the quantum squeezing Hamiltonian. X and P have to be symmetrized, so it's Hermitian, blah, blah, blah. Let's just do classical physics. This is the squeezing Hamiltonian for an oscillator. Remember Hamilton's equations of motion. X dot is dH dP, which is Gx. P dot is minus the force minus dH dx, which is minus Gb. The solution is x of t is e to the gt x p of t is e to the minus gt p. So if I started, think of like a classical ensemble where I might be here, here. Wherever I am, okay. And make G negative, then X gets squeezed and P gets anti-squeezed. Okay. So if you solve the Heisenberg equations of motion quantum mechanically for this Hamiltonian, that's exactly what happens. Okay. So that's how we're going to generate. That's how these, well, you know, if that's how a theorist would generate this. As I said, the experimentalists take big finite steps, but in this BCH expansion. Okay. And it's conditional squeezing. with squeezing or anti-squeezing, depending on the state of the qubit. Just for an extra twist.
X times p, you can write it in a different coordinate system, that's x squared minus p squared. You rotate by 45.
Yeah, then that squeezes.
The stiffness increases the stiffness of x squared and reduces the stiffness of p squared.
Yeah.
Right, so then it stretches your,
The other way, it does the other way around. Yeah.
but, you know, the x and p have different units. So like, there's already an arbitrariness. You know, when you say something is a circle in xp.
Yeah,
That's in terms of the units of p naught and x naught.
yeah,
It's a circle, but so there's already an ellipse.
yeah.
So why is one ellipse better? You know, there has to be some, you know, you've now created another ellipse in a different coordinate system that is stretched compared to the original ellipse, but there's an arbitrariness.
Yeah, it's you know, the whole thing is actually rotating around at twice the cavity frequency, so 10 billion times per second. So, you know, so the axis choice is just sort of depends on what your phase reference is of your master clock. Okay, all right, so there's some more about control. Now we have to do measurement. How do we get those fancy Wigner function plots, do state tomography, for example? Well, let's start with something simpler than the Wigner function, the characteristic function. The characteristic function is the expectation value in the state of an unconditional displacement operator. Or it's the overlap of a displaced version of the state with the state. Okay. So how do I, it turns out that this tells you everything you need to know. It's equivalent to the density matrix. It's equivalent to the Wigner function. So how would we measure the overlap of a state with a displaced version of itself? Well, you know, if you displace the state, you no longer have available the undisplaced copy to compare. You know, what you could have two copies and do the swap test, but what you should do is do a superposition of both having displaced it and not displaced it, or in this case, having displaced it by plus alpha over 2 or minus alpha over 2, depending on the state of an auxiliary qubit. And so you apply this conditional displacement with the qubit in the plus x direction. This unitary will kick back some phase, and when you measure the state of the qubit, it turns out that if you, the average value of sigma x, if you measure sigma x, that gives you the real part of this quantity. If you measure sigma y, it gives you the imaginary part. Well, how can I understand that? Well, crudely, you look at this and you say, oh, this makes a displacement of the oscillator whose sign depends on the state of the qubit. But another way to say it is, oh no, this is e to the I theta sigma z. It's a rotation of the qubit around the z axis. The cavity is actually acting on the qubit. And the amount of rotation depends on where you are in phase space. So that's some way to sort of understand this phase kickback that rotates you away from the x direction towards the y direction and gives you these quantities. Okay? So you can, you know, you can work through the details of the wave function and show that these are true, but I'm just trying to give you kind of an intuition. Question? Yeah. Okay, so that's called the characteristic function. What's the Wigner function? Well, the Wigner function is a function of a complex parameter beta that tells you where you are in phase space. And it's kind of a Fourier transform of the characteristic function. And it's also kind of a Fourier transform of the Wigner function, of the, the density matrix. And this is the theory. What it is in an experiment is you displace the state and you measure the average of the photon number parity. And there's a bizarre identity that connects these two. And, it's just a bunch of algebra. Okay, so the Wigner function is quite nice. Here is a Schrodinger cat. It's a superposition of coherent state alpha and minus alpha. And you can see the vacuum fluctuations right there before your eyes. And this is experimental data. This is the 0-point fluctuation of the magnetic field, electric field. And in between, you see the whiskers of the cat, all of these interference fringes, and the color in the center, which says the parity when you don't display. Oh yeah, so what does this mean? What does this picture mean? You to get the Wigner function at this point, you displace to the origin and measure the parity. And if you don't displace at all, the red is even parity, and this is also even parity. So this is an even cat. It's alpha plus minus alpha. It's only made of even photon numbers. You can also make an odd cat where the fringes would be blue here in the center. Okay, so it proves it's not a mixture of two coherent states. It's a coherent superposition of coherent states. Okay. We were very proud at this time to make one of the largest cat states in the world with 111 photons. But now Serge Rosenblum has gone crazy and made one with 1,024 photons. Really amazing. This is the Wigner function, and it's a kind of quasi-probability distribution. It's positive in some places and negative in some places. And because position and momentum don't commute, you can't have a real probability distribution. Okay, the way you measure this point here is +1, it turns out, that red color. The way you measure it at this location, alpha, is you displace the state. I possibly have a sign error here. You displace the state back to the origin and measure the parity of the displaced state. To measure the Wigner function at this point, you displace the oscillator back to the origin and measure the parity. And
how do you measure the parity? Sorry, I did expectation around the parity related to
so I that same dispersive coupling I showed you on the first day, I think. You put the qubit in X, and if the photon number is 0, it stays there. If it's 1, it rotates by pi. If it's 2, it rotates by 2 pi. Right, so you measure the state of it's a phase estimation. It's 1 bit, it's the least significant bit in the phase estimation algorithm, which is the one you want, the parity. Good. Yes. Oh, thank you. That should be beta, or that should be alpha. It's all relative, as someone once said. That was a question here. Yeah. So this function is changing sign. It's oscillating. In fact, this function is precisely the two-slit interference pattern between a slit here and a slit here. The further apart the slits are, the faster these fringes oscillate. It's even that the slit has some opening width which causes them to damp out after a while. It's precisely that. Okay, so if I want to measure the Wigner function right there, it's going to come out to be negative. The way I do that is this is a point beta, let's call it. I need to displace the oscillator by, I think I should have put minus beta there. I displace that point in phase space to the origin, the oscillator, and then I just make the parity measurement. And I get plus or minus. Then I do that 1,000,000 times and take the average. Does that help? Yeah. Good. Other questions? Yes. Yes. Tornado. Oh, okay. Okay. Yes, so there's you know, there could be hundreds of millions of points taken there if you really want to do a good job. But we can do them pretty fast. So. Okay. Great. So these are the even and odd versions of the cat states, and they're made of even or odd photon numbers. And then our friend and competitor, Jonathan Holm, in the ion trap world, also makes large cats and also does GKP experiments. So we're in friendly competition with him. Okay. All right. Well, that's fine. Wigner functions are nice to measure, but what if I just want to know the photon number distribution, which we're going to use in the molecular simulation experiment, okay? I want to figure out some way to do what's called boson sampling, efficiently find out the photon number distribution. And the way we're going to do it is with like binary search. So, you know, I have grandkids, and when they were younger, you know, and you play this game of 20 questions, you know, and you think of something and they get to ask 20 questions. And instead of saying, or like let's do something simpler. I think of a number between 0 and 100, you know, you get to ask me questions. So they ask, like, is it 29? You know, no, right? Instead of saying, is it bigger than 50 or smaller than 50, right? That's the most efficient thing you can do. And then in log n steps, you find the answer, okay? By simply finding the bits in the binary representation of the answer. That's what we're going to do here. Okay. So let's start with the grandchild way of doing it. There's a question, is the photon number equal to 1? Yes or no? It has a 1-bit answer. I can map that 1 bit onto the state of an ancilla qubit and measure the qubit and get the 1 bit of information, okay? It's pretty inefficient. I'm going to do an experiment with 256 answers. And saying, is it 17? Is it 18? And that's pretty slow, okay? But let's at least figure out how to do that simple case first. So how do we do that? Well, remember, we have our friend, the dispersive coupling, which spreads out the spectrum of the qubit. And when you apply a pi pulse on the qubit at this frequency, it will flip the qubit from 0 to 1 if and only if there's exactly 1 photon in the cavity. Then you measure the qubit to see if it flipped. I talked about that on the first day. And that answers the question, is the photon number 1 or not 1? If the answer is yes, it is 1, the cavity state, whatever it was before, has collapsed to Fock state 1. If the answer is no, you get some really weird state, which is the same as before, except the amplitude for 1 is now missing. And then all the coefficients got changed and rescaled to make the normalization 1, okay? That can make some very interesting non-classical states. You could start with a coherent state, find out there's not 2 photons in it, and now you have some non-classical state. Okay, so this gate right here, which is a conditional pi pulse on the qubit, conditioned on there being exactly m photons in the cavity, will answer, are there m photons or not? Okay, so it's equivalent to this. This gate is this unitary where I put the projector here on there being exactly m photons. I could, is it 13, yes or no? Well, then I pick a different frequency that will flip the qubit if there are 13 photons. Yeah. Okay. Yes, I mean, you don't, it can't be too fast. If it's too fast, it'll have a frequency spread and it'll overlap. So there's a speed limit set by the dispersive coupling chi. So, I don't personally apply the gate, but my genius experimental friends do, and they seem to make it easy. I don't, it seems easy. Okay. As we all know, in theory and practice are the same, but in practice, they're different. Okay. So now let's ask a trickier question. Is the photon number equal to 1 of 1 or 3? That is it either 1 or 3, and I don't care which, yes or no? Well, then I just apply 2 tones. And the qubit will flip if the photon number was 1, and it'll also flip if it's 3, but nothing else. And again, my qubit gives me 1 bit of information. I find out that the state has collapsed to some superposition of 1 and 3, or a superposition without 1 and 3. Okay, so it turns out by applying all kinds of different combinations of tones, I can measure any arbitrary binary function of the photon number distribution. I can flip the qubit if the photon number is 0, 2, 4, 6, 8. That's another way to measure the parity. Or I could choose 0, 1, and 17, any binary. What do I mean by that? I take this set of projectors onto photon Fock state M, and I dot it, I have coefficients which are make a binary vector consisting of 0s and 1s. Yes?
It's the fact that the qubit is entangled with.
Well, the projector is by the frequency selection.
Right, it's the frequency selection plus the fact that qubit state is entangled, or qubit frequency is shifted by the
Yes,
number.
right, exactly. You need that the qubit frequency has to change with photon number, and then you select. Yes, excellent. Okay, so here's how I'm going to do my binary search. I'm going to apply tones that will flip the qubit if the photon number is in the upper half of the list. Then I'm going to apply, that's here, and I'm going to measure. Remember, it's a Q and D measurement. I don't eat up any photons in measuring this, this kind of super parity. Then I'm going to measure, if you're in the upper half, are you in the upper half of the upper half or the lower half of the upper half, et cetera, until finally, are you even or odd? Okay. And these measurements, it's literally a binary search to look for the photon number. It takes only log n depth. In this case, I'm going to do, I have 2 to the 4 possibilities. And it's pretty tricky because I have to do this unitary, make the measurement of the qubit, then do the next unitary while the cavity, everything is still coherent. I have to do that 4 times. Everything in the cavity has to stay alive. The qubit has to not have any errors during this. and I've done essentially the Walsh-Hadamard transform, or I get a sequence of 4 measurement results, and from those measurement results, A0, 1, 2, 3, I can calculate the bits in the binary representation of the number. If the each time, why are there these additions mod 2 here? Well, this comes out right, saying yes or no. This one, if this one comes out the same as that one, then it was a no. If it comes out opposite to that one, it's a yes. I don't reset the qubit to 0 each time. So that's why you have to do this modular arithmetic. If it didn't flip, the answer is no.
Meaning it's not that many, it's not that pattern of photons.
But when I say didn't flip, means I got the same answer as last time. That's why you have to do this. If you want, just pretend that I reset, after I get the answer, I reset the qubit to 0 and ask, is it 1 or 0? That's fine. Okay, and the circuit cost is only log of the maximum number of photons that you're going to allow yourself to distinguish. And this is exponentially more efficient than asking, are you 0, are you 1, are you 2, are you 3? Which is linear in Nmax. Okay, all right, so now those are all the tools. Oh, yes.
Just to make sure I understood this, so you need a number of different tones to produce each of those masks.
Yeah.
So be more efficient to, instead of doing the same set of masks every time, condition like what tones you're using based on previous measurement result. Like, for example, if you get a 0 on the first one, then you don't need to add tones.
Yes, okay, that's actually a good idea. I'm lying to you a little bit. They don't literally just put tones there. They do some optimal control theory, great numerical optimization of all those tones because there are stark shifts and overlaps and blah, blah, blah. I'm telling you kind of in spirit what they're really doing, but that's actually an interesting idea. If I know it's in the upper half, there's no point in applying tones down here, which might limit some of the damage and improve some of the fidelity. That's actually an interesting idea. I don't think they do that.
Boson sampling is you're trying to figure out what is the probability of n.
Yeah, I'm sampling efficiently from the boson number distribution. The phrase boson sampling actually comes from this problem. You have a whole bunch of beam splitters, and you put in, if you put coherent states at the input, it's trivial to compute the coherent states you get at the output. It's just some small matrix multiplication. But if you put Fock states at the input, and they get all mixed up by the beam splitters, it's very complicated, very computationally expensive to calculate the probability of getting a particular Fock state distribution at the end. And this difficulty, which involves calculating permanence of the propagator through that array, is the basis of that was proposed by Scott Aronson for quantum supremacy challenge using a boson sampling experiment. It turns out that the experimental simulation of these optical spectra is a lot like this problem, a slightly modified version called Gaussian boson sampling, where you put squeeze states, and squeezing is involved rather than just Fock states. Okay. All right. So before we do our very complicated triatomic molecule with 2 modes, let's just do a diatomic molecule. And here's the chemical bond. It's kind of a creaky spring. And let's imagine that when the bonding electron is ejected, all that had the spring constant stays the same, but the equilibrium position changes. It probably moves further away because you removed a bonding electron that's trying to suck it in. So what you have before you start, you have the motion, let's say the A is infinitely massive. B, the proton is moving in a harmonic well, and let's say it's in its ground state, the zero excitation mode. And suddenly the Hamiltonian is changed to this new potential well. So I need to, it's no longer in the ground state of that potential. And so as a result, you have to project the old eigenstate of the Hamiltonian into the eigenstates basis of the new Hamiltonian. And you'll find some overlap with the ground state, first excited, second excited, third excited, fourth excited. Yeah.
Oh, you described it as green, but we only put it in the like potential energy surface of the electron itself.
Yes, that's right. Right. But we're approximating it as a parabola. And we will do that in our experiment also. So it's an approximation. So the spectral density, the distribution of the excitations that are left behind is given, the spectrum is given by this, where this overlap probability called the Frank-Condon factor is the, the amplitude that you end up in the nth Fock state. And the energy that's left behind in the system, because it's now ringing, it's some integer multiple of the oscillation frequency omega. And where did that energy come from? It's taken away from the photoelectron. It came in with 1,000 volts. Now it has 1,000 volts minus 23 millivolts or something. So you measure this guy to find out the spectrum of vibrations you left behind. Is that clear? So that's the cartoon version of the experiment. So how do we calculate? Well, so this is trivial to calculate analytically. We're not going to do quantum supremacy here. So basically, all you have to do is recognize that in the new basis, the old state looks like it's been displaced. It looks like a coherent state of this guy at position minus delta, because it's back here. The state hasn't had time to change yet. The Hamiltonian suddenly changed, but the state didn't. That's called the sudden approximation. And we know for a coherent state, you can expand this and get this Fock state representation. And if you write the average excitation number in the coherent state is alpha squared, then the spectral density, which is related to the square of this thing, is exactly a Poisson distribution, which becomes a Gaussian in certain limits, right? Okay. All right, so now how are we going to do a simulation involving two modes? So I have my triatomic molecule, I have the symmetric stretch, I have this bending mode, and the two modes are protected from mixing with each other by the mirror symmetry, the reflection symmetry. Okay. So they have quanta in them, the stretch quanta and the bending quanta. They're at some crazy frequencies determined by chemistry. We're going to simulate them, represent them by quanta of photons in the two different cavities, the stretch cavity and the bending cavity. And we're going to execute the unitary transformation from the old Hamiltonian basis to the new Hamiltonian basis and produce all kinds of photons in here, which represent the phonons that are produced in the molecule. Then we're going to sample from that distribution. So, and again, the reflection symmetry is destroyed if you break a bond on one side and not the other. Okay, and you can, if the electron has short enough wavelength to tell which side of the molecule it came from, there's no interference. You've broken that symmetry. So now the modes will mix. So here's the I forget, stretch and bending, And you see the old potential energy surface has its symmetry axes aligned with the coordinates. But the new one is rotated because I've mixed the modes now. I'm going to need a beam splitter to do that for me. Also, there's a displacement of the minimum in two dimensions, and the spring constants have changed, which is squeezing. So I'm going to need all of those things. All of these, I'm going to need a beam splitter to mix the modes, to rotate between the modes, squeezing, and displacements. And some of these things are more challenging to do in optics. And I've showed you we have all the tools to do them here. Okay, so here's the circuit. I have cavity Alice, cavity Bob, auxiliary qubits in each one, and a beam splitter that I showed you how to do last time with 4-wave mixing. So I have to initialize the initial state, could be the ground state or some Fock state or some coherent state, but in generally non-Gaussian state. I have to carry out this unitary transformation from the old Hamiltonian basis to the new one. There's some error checks that I do because that transformation is supposed to leave all the auxiliary qubits in their ground state. I throw away 5 to 10% of the data when that check fails. Then I measure the photon number distribution in each cavity with number resolving measurements. And I can do it the slow but accurate way. Are you 0? Are you 1? Are you 2? Or the exponentially faster but slightly less accurate way that I showed you. Okay, now how do you do that transformation? It involves squeezing, which we again use as coupler, squeezing of Alice, squeezing of Bob, beam splitter between them, some more squeezing, and some displacements, and then measurements. Okay. And the histogram of the measured photon numbers, I make a histogram and I get that spectrum of the spectral density of things left behind. And I know the energy that's left behind because I know the frequency of the two modes under the new Hamiltonian. So the frequency, the energy that's left behind is the number of quanta in mode A times its frequency plus the number of quanta in mode B times its frequency. And here's the result I get for water. So each of these black lines is calculated on a classical computer. It's the exact answer. It's basically just these, it's a more complicated version of this Poisson distribution. And the purple data points are the slow method of measuring the number of photons. So there's 0 to 15 photons in each cavity, so 256 possibilities. And I do all of those one at a time. I can do each cavity in parallel. And you can see pretty good agreement between the purple dots and the peak heights. We know the peak positions. It's just the height that we're trying to sample from in our histogram. And the L1 norm distance between the theoretical distribution and the ideal one, that distance is about 5%, pretty small in the slow case. And in the exponentially faster sampling, where everything has to stay coherent for 4 measurements, it's a little bit worse, but still only about 15%. So that's a measure of how close the distributions are. Okay, questions about that? Yep, Anusha. Up. So this is literally the spectrum of energies that the photoelectron has that the chemist would measure, because it tells you how much energy was left behind in vibrations in the molecule and taken away from the kinetic energy of the photoelectron. So this is literally the thing the chemist would measure. So this is a simulation of the experiment that the chemist would do. The chemist is also sampling and gets a number in each mode each time they do the experiment. But if you wanted to not do the experiment and build a simulator to do it, then the binary search method would make the simulations run exponentially faster. Well, what we did was we actually collaborated with chemists. You saw some, see, you can tell we're collaborating with chemists because nobody in their right mind uses that unit. But they, they did the local density approximation, classical calculations to find the bond dimensions and the curvature and the potential. We approximated that surface as a parabola from their numbers, and then calculated the theoretical spectrum we should see from their numbers, and then did the experiment to compare.
They looked at the ground state with one less electron in it.
Yeah, they
I guess the
the electrons respond adiabatically to the slow motion of the nuclei. Yeah, so the potential surface effectively changes instantaneously. That's the argument. Yeah. Yep. Yeah, so let's see. So, okay, wave number is energy. So this is higher energy of the electron, and so there are fewer, I think this is the fewer vibrational quanta left behind. And this is more, so that's probably why it is. That's a good question. I haven't thought about that. We thought it was pretty good, but yes, it is off.
So I guess I'm wondering what's left to close the gap.
Yeah, so in that quantum non-demolition thing where you have to do 4 measurements, the cavities have a little damping. It takes some time. The measurement fidelity of that mapping the parity to that 1 qubit. When you measure the qubit, sometimes you make a mistake. The qubit is the worst thing here. It has the shortest lifetime compared to the cavity. So sometimes it falls down and messes up the measurement. Also, when it falls down in the middle, it messes up the subsequent, if it happens in the first time, the subsequent 3 Q and D measurements are a mess. Yeah. Yeah.
You mentioned the sampling method, you need to do for 4 measurements. Isn't it the case that when you only measure the single bit, you need to measure 100?
Yeah, the exponential in this case is 32, I think.
So it's just even more complicated. So why does it happen?
Maybe I don't understand the question. I'm saying this takes 32. This takes 32 times longer, but it's more accurate.
The second method gives worse data quality because the measurement is complicated.
Yes, yes.
But the first one is even more complicated. It needs 32 measurements.
No. It's very simple measurements. It takes many more shots. Many more shots, because if you ask, is the photon number distribution, it's between 0 and 255. Is it 137? Most of the time, the answer is no. So you're not getting much information per shot. But the measurement, the answer, yes or no, is more accurate. And if you just are willing to do the experiment many more times, you end up with better data, but it takes longer.
Each individual experiment only measure 1 point.
Yeah, right.
That is converted into a sample complexity.
Exactly. The sampling complexity is worse, but each sample is more accurate. Good. Okay, we're out of time. I'll just emphasize you can't do this with typical photodetectors and optics that eat up the photons. They're starting to be able to do some photon number resolution, but not on the 0 to 15, as was done here. And we just very efficiently get the 8 bits representing the 4 bits of the binary number in each cavity. We've also done, so it turns out if you try to do this on a qubit computer, it would take dozens of qubits and gate depth of 1,000. So we have demonstrated supremacy over not classical computers, but all existing quantum computers. Okay, you can also do, in your eye, there's a thing called retinol, vitamin A. It lives inside the main molecule that makes your eye work. And the potential energy surfaces actually have no gap. They intersect at a point, a conical intersection. And when you get excited up here, whether you fall down here or over there is whether you see the photon or not. And the molecule undergoes a conformational transformation that catalyzes your optic nerve to fire. And so that Chris Huang also did a second experiment, way too complicated to explain, exploring this dynamics and the role of the breakdown of the Born-Oppenheimer adiabatic approximation here, and the role of environmental dissipation in the dynamics. So I'll thank the experimental group and our friends, the actual chemists who helped us do this, and Ike Chuang, who helped us show that a qubit-based quantum computer couldn't have done this, and also thank the Deveray lab with whom I work. Thank you. So I think we're a little late, but we can have a few questions. Yeah, so that's the second obnoxious question. So no, we didn't compare it to experiment because we made a fairly significant approximation in assuming that the surface was parabolic. And the next experiment I would love to do is to synthesize the anharmonic potential where we can't use this simple trick of just executing the unitary transformation. We have to do phase estimation on the time dynamics of the new Hamiltonian. So much harder, but I'd love to try that as a future experiment.
Experiment, see fine structure.
Yeah, I mean, well, even in triatomic molecules, I mean, they mostly do big molecules, but then it's very complicated and it's chaotic essentially. Yeah.
Oh, for the experiment, the breakdown of Born approximation, do you include electron bonding?
Well, so the idea is you're in some electronic state and some position of the nuclei. You solve the Schrodinger equation for what the ground state of the electrons is, and then the proton or whatever moves very slowly. But if there's no gap in the electronic spectrum, then when it moves near that conical intersection, you get non-adiabatic, essentially electron phonon coupling becomes very important. No, we made that Hamiltonian and we made it have a conical intersection as a function of the coordinates of the oscillators.
So you have some cavity qubit coupling.
Yeah. Yeah.
So, yeah, I'm sure going back to boson sampling. So I would have thought like an efficient way of doing it, rather than sending individual pulses, send something very broad and just broad pulse at all frequencies and just see absorption of it. And that
Right, but we don't have a way of detecting the loss of a single microwave photon by absorption from a pulse. That's why we do quantum jump spectroscopy. We have a good way of seeing that the photon was absorbed by the qubit because the qubit changed state, but we don't actually have a way of detecting directly. Yeah. We do quantum jump spectroscopy, yeah.
Okay, but if you do it that way, like individual pulses, like how, if it did flip, then you know, okay, you had that many photons corresponding to that
Right.
frequency flip.
Right.
if it didn't flip, now you have some other wave function. Now
Yeah.
You put in some other state.
So then we flush everything out and start the experiment over.
Oh, so you post-select
You,
on only
yeah,
always.
yeah, you could go through and say, are you 0? Are you 1? Are you 2? Are you 3? Because asking that question doesn't change the photon number, doesn't eat up photons. You could go through, but we don't do it that way. Yeah. But you could. One last question. Okay, time for the photo. Everybody get up. Don't make Leo mad. Follow Leo.